the applied force, okay, different color. The applied force is parallel to the centroid. Okay, that is the difference. Okay. Previously, let's look at the difference between eccentric and centric. Previously, when we do centric loading, okay, centric symmetrical loading, right? So I'm going to draw this out, okay? So transformation still the same. I want you to see the difference. X and Y rotation about Z, right? We used to have this, right? So we have a structure. One end is pin. The other end is on a roller, and we apply a force P over here, right? So when we calculate our moment, we know that this is P over 2. This is also P over 2. The moment we calculate, so if this is point C, the distance is L over 2. So our moment in Z, right, is equal to PL over 4. I'm going to now draw the centroid out. Okay, so let's say it's rectangular. Our centroid is in this direction. Right? So this is our centroid. So for this case, what we see, right, is the applied force is perpendicular, okay, perpendicular to the centroid. Okay. So that's why your moment is PL over 4. Okay. For this case, for what I'm teaching now, the applied force that I'm circling now is parallel to the what? To the centroid. Okay. And this is where we have to be careful. When that's the case, the moment in Z, right? So mz now is equal to P multiplied by what? D. Okay. D is the perpendicular distance over here. Okay. G is here. Ask a question. What if the question gave us the stress and asked us to determine the moment? Geza, which question are you referring to now? Can you speak? Hello? Okay, someone online asked, what if, right, we are given the stress and to find the moment, right? So if we are given the stress, for example now, let's say we are going to find for aluminum, right, mz y over izz, and this is equal to minus 600 megapascal or psi. Okay, so we want to find mz. The question by the student, if the stress are given, how to, so all you need to do now is mz is equal to minus 600, right? Multiply by, so because both sides are negative, right? So it will become positive. So it's good. 600 multiplied by y is, or 600 multiplied by IZZ is 156.083. Then divide by your y, which is equal to 3.475. And then that's divided by 1. So this will be equal to 600, 156.083 divided by 3.475 divided by 1 is equal to 26,000 or 26.95 times 10 to the power 3 pound inch. Gazelle, I hope I pronounced your name properly. Okay, so it's just moving equations around. It's not that complex. You agree? Okay, he says thank you, and I say thank you also. Right, coming back to here, right? So the difference is our moment down here, right? You can see the moment is P times D, right? D is the distance to the centroid. If you look at centric loading now, right? The distance is to the what? To point C. Okay. The distance is to point C. Whereas over here, the distance is to the what? To the centroid. Because moment is equal to force times perpendicular distance. Okay. Now, we are interested in C, this region over here, because this is where failure will occur. Okay. So when you see where their failure will occur, okay, what is happening in point C? Okay. So point C, we know there is a moment. Point C is the point of interest. So if again I draw a horizontal line, right? This is our, so at point C, we have a distance from here to here. We have a perpendicular distance. So we have a moment m prime. So apply Newton's third law, action equal reaction, same in magnitude, different direction. We also have a counter moment over here at point C. And then we have an axial load, axial force in the x direction in P prime. We have a reaction that is our F. Okay. Again, Newton's third law, action equal to reaction, same in magnitude, different in what? Direction. Okay. So now let's say I'm going to sketch for you how does the shear force, how does the normal stress distribution look like now? Okay. So we are aware that this has two components of an equation. Okay. We know that we have stress X is equal to Pz over A, Px over A plus by mz over izz multiplied by y. Okay. So now we are going to draw the cross-sectional view. Okay, we're going to draw the cross-sectional view. We are going to follow this notation over here. Okay. I'm going to string this. Okay. So if I were to draw a transformation, this is our x, y, rotation about z. So now we are going to look at a cross-sectional view at C. So what we have now, for example, for simplicity's sake, I draw this as a rectangle. Okay. So based on transformation, now this is your y, z. This is our rotation in an x. Okay. So I'm going to sketch the stress distribution now. So this is our normal stress in the x direction, right? This is our y, right? So we're going to sketch stress x is equal to px over a. Okay? So when that's the case, we have a vertical line. At this point, it corresponds to px over a in tensile, and this is how the stress is going to distribute. Okay, up to here. Okay, so this is due to our axial load. Now I'm going to sketch our stress field, okay, due to the bending moment. Okay, so this is our y, this is our stress x. So now stress x is equal to mz over izz multiplied by y. Okay, so based on this loading condition, right, we know the top, due to the moment vector, we know the top is going to be compression, the bottom is going to be tensile. Then now we sketch the stress distribution again. Okay, so this is compression, and this is our tension. And this value over here, and this value over here, this is our positive stress X max, and this is our negative stress X. Okay. Now, if we were to add both of them together, how does it look like? So if you add both of them together, it looks like this. So this is a Y, this is our stress X. Now, watch what I'm doing, okay? I'm going to copy the slope. And all I'm going to do now, so the slope is the same, I'm going to shift it over. Okay. So this will be equal to stress X mz over izz. Oh, no, I missed something. So this will be equal to px over a plus by mz over izz multiplied by y. Okay. Okay. So Noah, what do you mean by its slope intercept form but for stress? I don't quite get you, Noah. Can you speak up? The student Noah say it's slope intercept form but for stress. It's okay, Noah. Let me sort you out later, okay? Or if can you speak, Noah?
Can you hear me?
Yeah, we can all hear you at class. It's like you're face to face.
Okay. All it is it's y equals mx plus b, but we're switching around how we do it. All I see here is a straight line with a y-intercept and an angle. I mean,
yeah, that's correct. Nothing wrong with that. That's the right remark, okay? But there's something that changed. Okay, Noah?
I'm not sure quite what, but okay.
I'll show you what is changed, okay? Be patient. You are like wanting to know what happened to Luke Skywalker in The Empire Strikes Back, you know? So what you see over here is this, okay? So on the, I want you to focus on the both diagrams, okay? Over here is what we have is known as centric loading, right?